Vikram, can you check YouTube? Coming? Done. Good afternoon to all the participants. I welcome you all for the afternoon session of this short-term training program on drivers of Industry 4.0. So in the afternoon session, we have amidst us Dr. K. Sendil Kumaran. So sir will be delivering a talk on connected systems, a smart manufacturing perspective to the fourth industrial revolution. Now I would like to invite Dr. P.B. Shetty sir to introduce the speaker.
Good afternoon to everybody, participants, and our speaker of the day, Dr. Senthil Kumaran sir. Dr. Senthil Kumaran is currently assistant professor in Indian Institute of Information Technology, Design and Manufacturing, that is IIT DM, Kanchipuram, Chennai. He obtained his doctorate in additive manufacturing in mechanical department of IIT Delhi. He previously worked as a guest lecturer in Systems Integration Division of National Institute of Standards and Technology, USA. His research interests are in additive and sustainable manufacturing. He is associate editor of ASTM Journal on Smart and Sustainable Manufacturing. He is a member of ASME, SME, SAE, and IEEE. He is also a member of IFIFE WG 5.7, developing smart manufacturing technologies. He has been nominated for prestigious in-residence program for inspired teachers at Rashtrapati Bhavan during 2016. He has more than 30 international publications in peer-reviewed journals and conferences. He is also a regular speaker at various design and manufacturing workshops and events on design and manufacturing. He has taught more than 10 courses on design and manufacturing and maintains an online portal called manufacturingportal.in for blended learning in design and manufacturing education. As part of outreach activities, he is also the coordinator for Teaching Learning Center at IIIT DM, Kanchipuram, funded by MHRD India, which develops extremely affordable digital fabrication technologies for colleges, polytechnics, and schools of STEM. He is also in charge of the design and additive manufacturing lab at IIIT DM Kanchipuram, funded by MHRD India. Before I hand over to Dr. Senthil Kumar, I like to mention here that our college students visited IIIT DM and manufactured Industry 4.0 product with the help of TLC of IIIT DM. I do not know whether sir remembers or not. We along with our HOD visited IIIT DM. Our HOD was Dr. Sudhir Reddy, visited IIIT DM in the last year and had a meeting there. At that time, Professor Pandyan was in charge of TLC. In memory of that, we have brought one this acrylic cut tea from I don't know whether Dr. Senthil Kumar sir is able to see or not. Sir, are you able to see? Yes, sir. This is the one which you gave on the we took from your TLC, as well as we got one 3D clock key bunch. So that's very good and a very small machine manufacturing all these sort of things. So thank you very much, sir. I will now hand over to call upon Dr. Senthil Kumaran sir to go ahead with this presentation. Thank you, sir. Thank you.
Okay, thank you. So I am just starting to share my screen. So you can just tell me whether you are able to see my screen. Just give me a second. Yeah, I think so. You need to allow me to share my screen. Right now, I don't have permission because I'm joining from a different domain. So could you please
Yes,
give me a permission to?
sure, sir. We'll do that. We'll do that. Share screen. Sir, it is enabled, sir.
Thank you. So I hope all of you are able to see my screen.
Yes, sir. We are able to see it.
Okay, so I would like to begin my talk with. First of all, I'd like to thank Professor for remembering his visit at DDM, and then we met at the Teaching Learning Center. So Teaching Learning Center, um, I think had I think engaged with NITI for developing few machines and things like this. So there have been some discussions going on. So around that. So maybe I think we'll switch on the captions because it may be distracting. Okay. So there are two kinds of engagement that we had with NITI. One is a team of people from NITI who came here and had a look at our systems, and then we actually developed a model maker space. So the maker space is a maker culture. Like in Western world, people call this as a maker culture. So where teachers come together to create experiential learning of STEM kits. So we have been supporting many schools and many colleges to develop their own makerspace. So we offer research-based consultancy services, as well as we handle them in case if they want to build their own machines. So we have a DIY, most affordable machines that they can build in our facility. So we have a full workflow for building a new machine in our facility. So that is the engagement that we had at PLC. But I'm also taking care of the Center for Smart Manufacturing. So that is also my one area of interest that I work on. So I started my work at NIST. So I was into additive manufacturing for the last 16 years. So around 2012, I think I got into this smart manufacturing, because that is the time around 2011 when the first Industry 4.0 document was released by the government, German government. So I think before I would like to go further into this particular perspective of fourth industrial revolution, I think many of you might have already attended my talk in some other places, because I usually offer a very similar talk in many places, because this is a very nascent stage Industry 4.0 there. Okay, so now this is a very important topic that we today discuss. But before I wanted to go deeper into the topic and understand, I want to understand a few perspectives from some of the participants. So you don't have to unmute your mic, but what you can do is just leave your comments in the chat box about your experience of, let's say, how much you have knowledge about fourth industrial revolution, whether you have worked at Industry 4.0 technology, whether you developed a product or a process or a system or a point solution around I4.0, you can share it in the chat window. Also, you can have questions. I think I will try to address those in between also, because I want mostly an interactive type of a session, mostly interactive participants most of the time. So before I begin my talk about fourth industrial revolution, as I said, I had a very short stint at NIST. That's when I came to know about smart manufacturing and fourth industrial revolution around 8-9 years ago. So then around 2015, we started a program in BTech Smart Manufacturing, which is a fully compliant Industry 4.0 curriculum in our institution. So then around 2017, we started our MTech in Smart Manufacturing. So the first batch just passed out, the BTech Smart Manufacturing. So they had IT plus OT. IT means like industrial, the information technology, and the OT is operational technology. So IoT is about IT plus OT. So we had a very good curriculum. I think I come from an institute, Indian Institute of Information Technology, which is situated. So I think I would request other participants to mute their mic, especially also the organizers. Prashant, could you please kindly mute your mic so that so it will be legible, and also it will be audible for others. So Great, thank you. So now, so one of the things that I wanted to tell you about my experience with Industry 4.0 is like when we started the program in 2016, we consulted many industries. Like we are at a juncture of IT and automotive cluster. So in Chennai, so we are situated in Chennai, even though the name is Kanchipuram. So we are in Chennai. So we have a OMR where we have this entire IT companies, and then we have the entire automotive belt on the right hand side, and then IT belt on the left hand. So we are at the sweet spot between like the manufacturing and the IT. So which is what I 4.0 is all about. Okay, so what I'm going to do today is to tell you about few important things. What I'm going to cover in today's topic. First is about the challenges. So I think I have. I want to discuss first about the challenges, and then I wanted to basically tell you about the global and Indian perspective. So then I would like to tell you about the convergence of technologies, and then the business drivers, and the reference model, and the enabling technologies, and the benefits of implementing something like that. So before I begin, I would like to basically tell you a bit about this particular aspect. So let me just give you an idea about what is, what are the challenges that that India or global perspective. What is the need for Industry 4.0? Why we are talking about connected systems now? What the world is increasingly, what is the new normal, and then what we are trying to basically do. And one of the very important understanding is the drivers. I think this particular workshop is all about drivers. So you are going to see the business drivers as well as the technological drivers for Industry 4.0. We'll cover that. And also we will have the reference model. We will talk about the reference model. And then also we'll discuss about enabling technologies and the benefits towards that. Okay, so now, so let me just tell you about what is the challenges that industry is trying to face. Right, so one of the important challenges that industry is trying to face as of today is about this, adapt or perish. So there is a very important quote from H.G. Wells. I think it's about adapt or perish now as ever. It is nature's inexorable imperative. So that means we have to constantly challenge ourselves and innovate ourselves to move from conventional practices to the new practices. Right. So what are the challenges that really industry faces as of today? One of the important thing is like the fact it's becoming globally competitive today. So the factory assets, what we have, need to become really globally competitive. And also the cost, the capital, the operating costs needs to be lowered. So right now we are seeing a mountain of change in terms of the way businesses are looking at efficiency and then the cost, right? So there has to be, at some point of time, they used to basically have monopoly, and then they used to make a lot of parts, churn out parts after part, widgets after widgets. So there would be people who would be willing to basically take anything that the company offers. But right now, we are at a cutthroat competition. And so, and also the cost, the operating cost needs to be lowered. Okay, so before I tell you a bit about our narrative, what I'm trying to build today. So I'm not talking about this COVID-19, which will go in 1 or 2 years, or probably, which has its effect. Maybe in another 2 years. We are talking about 10 years, 20 years down the time. So we are talking about something which is revolutionary, not evolutionary. Evolutionary means like it takes certain time for the technology to evolve, but it is going to completely change the paradigm of how the things are getting manufactured and things like that. So we are talking about something which is a long term, right? So the manufacturing workforce with advanced training and skills will be a key competitive advantage. What does that really mean? Is like, so we are all coming from the educational background. So when we talk about industry, so why are we so concerned about industry? And also fourth industrial revolution, because we are training the workforce. So we are producing the workforce for people to work in the factories of the future. So now we need to understand that landscape. What is this landscape, technological landscape that is there? And how would we basically get ourselves, pull our shots together, and then probably, come back with things that could be really needed for the future society and future industry. Now, one of the things that I wanted to tell you is like there are good narratives that is coming up. So when we started this Industry 4.0 program, That was somewhere in January 2015, right? So when we started thinking about starting a BTech program, we called all the industry people here. So all the major automotive companies in and around Chennai. There are around 15 automotive companies, the big names. They are all in Chennai. So we invited every one of them into the table, like automotive passenger cars manufacturers, scooters, and motorcycle manufacturers. Then off-road, on-road vehicle like Caterpillar. So we have got plenty of good variety of automotive transportation sector people, and then we also got IT people. So we invited them and put them into the room and then discussed a lot about how to derive a curriculum and then go about this. So that is what we identified a lot of challenges in terms of training and skills that needs to be important to the people when they are going to work in the fourth industrial revolution or industry 4.4 factories. And we found out that there is going to be an stagnant in unskilled, high labor oriented jobs. So because people are going to hire people. So because the factories are becoming increasingly connected, they are also automated, and they are also becoming intelligent and proactive, and also they are becoming some collaborative, so things like that. So then people, a simple machine operator, you can see this guy, he's still working with a planar machine. So which is the thing of the past. So when you are not working with the latest technologies, when you are not talking about something which is of not very immediate use, then there is going to be a stagnancy in the job. So we thought like we should actually invest our time and energy into a new program, which can actually train engineers. The first batch has passed out and they were received in a very good way. I think I will share this experience towards the end. So like all the automotive companies nearby who came and they have recruited them, and then there's going to be a lot of the second batch is already into internship mode and they went into industries in spite of the COVID-19 also the recession. So they were able to get placed in many good places. That is about the teaching part of the story, right? So starting a program in Industry 4.2 curriculum. So I was the one who launched the program along with our director. So we had smart manufacturing coalitions, which is from the US. So one of the smart manufacturing innovation institute person came here and inaugurated and things like that. So those are some of the narratives. So, but these are the challenges. But let us look at how Indian industries or any industries are positioned to take care of this particular aspects of Industry 4.0. So you see that there are two important axes that you see. One is the favorable drivers of production, and then there are unfavorable drivers of production. So you're talking about drivers, right? So which is what are the drivers for the future Industry 4.0 being applied? Now I think you all understand what is Industry 4.4, and also it has got a specific spelling, right? So the 4.0 is nothing but it's a fourth industrial revolution. So the first industrial revolution, I think you must be knowing that India was nowhere near during the steam engines and diesel engine and petrol engines. And second industrial revolution, during mass production, we were under British rule, so we were not able to do much. But the third, it's IT. So we are moderately did well to catch up with the IT revolution. But the fourth industrial revolution, how are we positioned? Is our industries really, is there any drivers from the industry? So what are the favorable drivers and unfavorable drivers? Because this topic, what we are discussing today, is about drivers for Industry 4.4. So what are those drivers? For example, one of the very important things that you need to understand is like there are, if you look at this 4 different quadrants. So the top 2 quadrants, there's a limited current base, but they are positioned well for the future. Like there is a simple and small structure of production. You also have a large and complex structure of production. They are really positioned well for the future. So you have 2 types of industries. They do really good potential for Industry 4.0. But there are unfavorable drivers of production. So there are people are at limited current base. They are also at risk for the future. They are very nascent. So and also there are legacy people who are very strong at current base but at risk for the future. So you can see that these are the unfavorable drivers of production. These are the favorable drivers of production. The Industry 4.2 applies to everyone. So now one of the things that you should understand is that there is something called as a capability maturity model. So if you look at all the Industry 4.0 white papers coming from the industry, you can take any good IT consulting industries within India. So they would have published a lot of white papers around Industry 4.0. They always talk about something known as a capability maturity model, something known as a CEMM. So what it tells is like what is the effect of whether the industry has any capability to apply, this level of automation or this level of, production scenarios and things like that. So we are always looking at from the manufacturing perspective. So when I say manufacturing, it's not about taking a raw material and converting it to finished goods. I kind of look at manufacturing from the BPM perspective, like where you have manufacturing industries like paper, fertilizers, chemical industries, pharmaceuticals, food and manufacturing, and then you have automotive, defense, space, consumer electronics. These are all called, even space and aerospace. They are all put together under a big basket of manufacturing, right? So I think you must be knowing that the country's gross domestic product (GDP) is usually measured as a percentage of manufacturing output. So manufacturing creates wealth for many nations. You must be also knowing that if you're good at manufacturing, then you create wealth. So because when the moment you take a raw material and convert it into finished goods, you're adding value, right? So that value is what we are talking about. So some noise. So yeah, I think Raghavendra, please could you please kindly mute this. Thank you. So some organizers can be little active. So the moment they see someone's mic is on, probably you can mute. Right. So now one of the things that I wanted to basically tell you is about the favorable and unfavorable drivers of production. So unfavorable drivers of production is about being not able to push him really well into the future. So rather, could you please kindly mute your mic? So organizers, if they are available, they can also mute.
Sir, yes, sir. Yes, sir.
So those who are organizers, they can mute the participants because it creates disturbance for others.
Yes. We're doing that. We will do that. Yeah.
Okay, so I think there is also a small, error here because I'm reusing some of the slides from my last webinar from May. I think there's some problem with the data, so I have not updated some slides may carry the old dates, right? So now, if you look at it from the perspective, so the perspectives are mostly coming from, looking at this from the capability maturity, how industry is really well positioned or not. Now, most of the industries that we talk about in India, so now they are also clustered into small and medium scale industries. They are also clustered into, high tech industries, right? So now we are talking about something like a Brilliant factory, so which is a Pune, like a GE's plant. And there are also plants which are also called as lights out factories. Lights out factory means like it is able to produce parts without having any human intervention. So it's completely automated process. Right. So now when we are talking about this capability maturity model, so some industries are really well positioned, even when they have a small structure or simple structure. And also many industries are working in a supply chain. The OEMs push their agenda into the supply chain. So tier 1, tier 2, tier 3 supplier has to adopt. So let's say, for example, if they want to build a traceability into the product, so they are trying to implement an IoT-based traceability along the supply chain. So everyone in that supply chain, the value chain also, it can be also called as the value chain, need to be updated to the fourth industrial revolution or I 4.0 compliant mechanisms. For example, you must have heard about UNCFACT. So UNCFACT is basically a standard agency which provides supply chain kind of data. So they develop a lot of standards around supply chain, especially in the logistics. So when you are sourcing components, the UNCFACT provides the proper encoding and decoding of data, and also supplier base. They want to basically understand how the supply chain can be, standardized in terms of even communications and then the workflows and data and everything. So like that, in the manufacturing stage, in the raw material extraction stage, maybe in the distribution stage, the warehousing, logistics, the use phase. So everywhere you want to basically implement Industry 4.2 to trace it, because you are looking at augmenting the entire production system with huge amounts of data, from capturing them from the entire life cycle, right? So that basically demands even the like small, limited current based simple structured industries. Like you have a lot of small scale industries in and around Bangalore, right? So those would be supplying components to OEM. So there is a push from the OEM to basically make them compliant with whatever standards in Industry 4.0 systems that they are trying to implement. So there is so industries are also moving, right? So now let us just look at the challenges. I think I discussed about two challenges. One of the challenges is about how the factories are becoming more competitive, and then we are also looking at challenges in terms of the job nature, how it is getting changed, and how people need to be trained. And also we talk about capex and opex, right? So the expenditures, capital expenditure and operating expenditure, so how they have to be lowered and things like that. Right? So okay, thank you. So now let's just move on to the global Indian perspective. So in this section, what I am trying to tell you is what the global manufacturing superpowers, what they are trying to do, and also what other countries like Europeans and the US and Australia and Japan, and also some of the South American countries, what do they do? So the US actually recognized the need for the fourth industrial revolution. I must tell you that I was there when these things were happening. So, and I'm also at the most happening place, NIST, which is the the one policy making decision for manufacturing in America. So most of these institutes, the projects, and also NIST actually established these institutes as like the funding was there from NIST to basically enable these institutes to come up and things like that. So I was at the most happening place that time, and the Industry 4.0 was policy making was happening. So I was able to understand it as an insider perspective. So I must be able to tell that the fourth industrial revolution or Industry 4.0, why it came into being existence. Now I must tell you that there is an aging population in Germany. So Germany thought that, I think if you look at our demographic population, so we are a very young country. So our demographics are really good. But if you look at, so that is also making the COVID numbers very less for us. Even though the ratio between the total population for 1 million population, our COVID inspection is extremely less. That's because we have a very young population. Whereas in Western countries like Europeans and US, you see there's an aging population, especially in Germany. So there are not enough people to work in factories. So the government thought that they should bring something to the level of automation such that the entire factory should run without humans. Right. So it is about creating new job opportunities for the machines rather than man. Right. So that is what the fourth industrial revolution is all about. So it is to cater to the needs of that. So, but there are a lot of questions within India. Like when I come to the Indian perspective, I'll try to answer that perspective. So what is happening here is that in the US, when they realized that Germany is doing something, they also wanted to start their own Industry 4.0 program, which they wanted to do it in their own way. So they called it as a smart manufacturing. So I can use the term smart manufacturing or fourth industrial revolution or advanced manufacturing sometime in an interchangeable way. So because different countries wanted to call their own policy. Because if you look at the spelling, even Industries 4.0 is spelled a little differently. So it is spelled to basically like RE, right? So that is typically a German spelling, so the dash spelling. Right? So it's a German thing. So when it is adopted or worldwide, so they had need for it to adapt. So why India really need to adapt it, and what is that India is going to do? Those things we will discuss. If you look at here, so DMDI is one institution which is called Digital Manufacturing and Design Innovation Institute. America Makes is another institute which is the first institute which came up. So I think so the PICASE, I think you must be knowing that Presidential Council on Advances in Science and Technology. So there's a council called PICASE Council. So they have met, during the Obama's presidency, they found that they need to basically establish several institutes in manufacturing which could cater to the needs of the Americans. So the American context was completely different. They wanted to bring back the jobs which are lost to China because they felt there is an unemployment which is happening there. So they wanted to basically invest in this technology so that they can be high skilled labor to bring back jobs from America so they can run the factories. These are some of the institutes that they have formed. America Makes is initially called as National Additive Manufacturing Innovation Institute, NAMI. So like that, there are so many other institutes which are there. Like you have flexible and hybrid electronics, and then you have photonics, then you have composites, you have power electronics, you have lightweights, like you have digital manufacturing and design innovation. And then this one is smart manufacturing, which is actually my boss, he is heading this particular institute called Clean Energy and Smart Manufacturing Innovation Institute, which is actually established by UCLA. So from there is something called as SMLC, Smart Manufacturing Leadership Coalition within US with Professor Davis from UCLA. He started that in 2011. Then it actually went into the Smart Manufacturing Innovation Institute. The thought process went into this. So now these are the things what US is doing. If you look at the European Union is trying to do so many things. For example, this is the top EU level, so general EU level initiatives. ICT for innovation for manufacturing in SMEs, which is called I4MS. Smart anything everywhere, digital sector, public-private partnership. These are some of the Vanguard and all those programs. These are typically called as the answer to Industry 4.0. Germany started this. This is called Platform Industry 4.0. Mittelstand 4.0, Smart Smart Autonomy for Industry 4.0. Right, so also it's called OWL, right? So Austral Fashion Lipi Alliance Industry 4.0. Some German names. Let's not get into this stuff. This is where it all started, Germany. So they gave this name Industry 4.0, and then it spread like Wi-Fi to other European countries. Now Slovakia calls it Smart Industries, Czech calls this way, and then Sweden calls this Production 2030. Denmark calls this the MADE, right? So Belgium calls this Make Different, and Marshall 4.0. And things like that. So there is a lot of European level initiative, there is a national level initiative, and there are some region level. For example, EPSRC on action plan, especially for Scotland, UK. But UK now left European Union. Now it is like after Brexit. I don't know what is happening there. The country is going into difficult times because of the Brexit. So, but let's not focus on political things right now here. So, but if you look at the world over, there is a manufacturing renaissance. So revolution and renaissance are the great, like far-reaching impact terms. So why we are using these terms to describe something which is happening there? The issue is like they are trying to basically relook at manufacturing from a completely different perspective. So they were doing things in a way that is far exceedingly, it's like meeting the new generation of things, a new generation of technology which has come, which is actually looking at the way the things are being done in a quite completely different way. So there's a paradigm shift. That's what we can say. So if you look at like the manufacturing renaissance, US calls it, and then you have productions have been made different, smart industry, high value manufacturing, right? So innovation 25 program, and then made in China 2025, right? So digital manufacturing for SME, industry 4.1 in Germany, right? So you can see different countries doing different things. India is also doing something called Make in India. I'm not sure what, it's a policy level thing to allow foreign direct investments in India and setting up manufacturing factories and making it India, but it's nothing to do with Industry 4.0, but there are some push with Niti Aayog and Make India working together to basically bring some wealth of knowledge into Industry 4.0, but I don't know. So that is more in terms of policy level things on Make India, ease of doing, ease of business and those things. That's what it talks about in variety of manufacturing industries. Now I think there is some effort that is going on like Atmanirbhar Bharat, which actually wants to bring back the manufacturing and production design into this thing. So a lot of things are happening around that place. Right, so now let us just look at the nature of the Indian industry, because we are talking about drivers. The entire topic the sessions that we are going to also talk about is about the drivers, right? So one of the drivers, why we need to basically look at Industry 4.0 from an India's perspective. What is the driver? What is the motivation for India to take up something like Industry 4.0? Because there is always this argument. I don't know whether you agree to it or not. There is always an argument that we say that automation is going to basically take away the jobs. So robotics and other things, when we implement, so human is going to be subjugated by the machine. So even people are talking about Indian context. We have too many people to work in the factories. So there's a growing unemployment. So do we really need to automate our factories? But if you look at our Indian industries, so this is look at here. So this is also a manufacturing thing. So he's taking a raw material and converting into a finished good by adding a value. So he sells at it. So now you look at a sophisticated factory like this is the GE Brilliant factory at Chakan, right? So Pune. So you can see that this is a BMW factory nearby Chennai, and this is also Make in India program. So what they do is like they bring it in courier. So all the parts come by courier from Germany, and then they assemble it here. And even if some scratches that you make on the part, then they have to send out to courier. So, but actually there is no manufacturing; it's all assembly. there's not even a single manufacturing thing that is available. Even the painting, reworking, they have to send it back to Germany. So, but right now I think they have some agreement with Force Motors to have some engines manufactured within India. But this is the BMW plant nearby Chennai, and we have other Ashok Leylands and Nissan, Hyundai, Caterpillar, Royal Enfield. We have Nissan, we have Ford, we have so many things. We have more than 15 big automotive names are making parts and cars, and then the inner and outer Chennai. So we have seen all these people. So, but one of the things that I would like to say here is like whether, if you ask me, this is my personal perspective, whether we should basically go and implement Industry 4.0. Is there any driver from Indian side to implement 4.0? Yes, there is a need. The reason being because so when we implement Industry 4.0, the job nature is going to change. Because when you are trying to basically implement automation, so your basic low-skilled labor becomes high-skilled labor. And also it is not that we are going to set up factories in India, but we are going to basically have the technology and then go set up factories in Europe. That's where they want to do, right? So we should have the technology and know-how to go to a place like where there is no workers and then put a factory there instead of we polluting here, right? So we have the know-how, we have the technology, we have the complete smart manufacturing suite of products, and then go and implement it in countries where there's a demography issues are there, right? So that is what we are talking about. So then you have an entire job creation at the high skill job. So we have a lot of high skill job that could be created instead of a low skill job. Right? We are looking at more low skill job right now in Make in India and other programs, but then we will be able to write so that the engineers that those who will be working in these factories will be nimble. They will have sophisticated skills of writing a program, operating a robot, and then changing the production schedules according to the demand changes, and then they can make a lean to agile to lean, and then lean to resilient kind of transitions between the production, and they will be able to operate, build factories of the future. So then they can also build factories which are ultra efficient, ultra productive, and ultra sophisticated. So the job nature is going to certainly change in the positive way. That is what I feel like it's going to help, because anyway, so we have always seen the technology actually enable more jobs than technology taking away the jobs. So that is the case. After IT, the service industry we are doing really well, but the manufacturing share of our GDP is extremely poor. We still have to depend on China and other places to basically do manufacturing. So that is the reason why I say Industry 4.0 is more relevant. There's a lot of drivers from the Indian perspective to basically move to the fourth industrial revolution. Okay, so I think I gave two important examples. One is about the challenges. So another one is about the global and Indian perspective. So any questions until this point? Is there any comments or questions about this particular aspect? So we are going to go change gears and get on with the technologies of Industry 4.0. So far what we have discussed is about the generic the need for Industry 4.0 and what other countries are doing and whether it is needed for India or not. That is the question we are trying to address. So any questions you can put up in the chat window, or you can also unmute your mic and ask one by one if you have any questions. So any questions?
Yeah, I request participants, to unmute and you can interact with the speaker. If you have any queries, please post it on the chat box.
Yeah, those who are on the YouTube also, you can post it. Maybe the maybe the organizers can look at it.
Yes, sir. We are monitoring the chat box from the YouTube also. We will be posting.
Those who are putting some questions in the chat box, probably the organizers can post it here.
Yes.
So I will be able to answer them.
Sure.
For the YouTube, those who are joining from the YouTube line. Okay, now so if there are no questions, shall we move on? Okay.
Yes, sir. We can move on, sir. Yeah.
Thank you. So now we will discuss about the convergence of technologies. Like what are the different convergence of technologies? So now let us just look at what is the world today. I think today, if you look at it, we are going through an unprecedented scenario. Like we are all locked down and locked up into our homes. So the schools are not opening and the colleges we are going through. So, but we are increasingly connected today. So we are connected increasingly, but we are not, I would say, physically connected, but we are connected together by internet, and we are able to exchange information, have a meeting face to face, and then collaborate and work and then operate factories operate industries, operate classes, right, schools, and then run government, right? So many things. So we have all this became possible because we are increasingly connected to the internet. Otherwise, it would have been very difficult for us to basically, shuttle between the paperwork between office and this thing. So we have, so we are increasingly a connected world. So that is making manufacturing a completely different perspective. So smart manufacturing or industry 4.0 is about all this 8. Now it has been become 12. So initially when they started, so these 8 technologies are considered to be the more important technologies, or so convergence of these technologies. But right now we have cyber security, and also we have other important things. So if you look at first one is the industrial Internet of Things. So, and then second one is we'll see one by one. So anyway, we are going to see all the technologies one by one. Right. So industrial Internet of Things, big data analytics, cloud computing, digital manufacturing, advanced simulation, advanced robotics, additive manufacturing, and augmented reality. So these are all independent technologies. They all have their own, kind of applications, and they have been there for many times. For example, robotics has been there for many years. Like the first robotics that have been employed, maybe in somewhere close to 1970s and 80s. So the factory started using them way before even 70, late 70s, right? So that what is so, what has changed now? Why suddenly people are saying these technologies are becoming revolutionary? Because there have been additive manufacturing or 3D printing is there for 30 years. So the first technology came into being around 1986, right? So why suddenly MIT comes back after 30 years and says that it's a revolutionary technology? And also data analytics. People have been analyzing data for very long. So for example, manufacturing applications of neural networks has been there. I think thousands and thousands of papers have been published in manufacturing applying neural networks. But what has changed now? What is so different than what is 30 years ago? So why it has become from evolutionary to, let's say, revolutionary technology? Why it is called a revolution today? That is more important to understand, right? So that is what I'm trying to tell you in today's class. Now, if you look at, so first of all, Internet of Things, right? We had initially an internet for computers, right? So I think Tim Berners-Lee started the World Wide Web, and then we are able to connect our computers through many standards, like we have TCP/IP and STTP protocols. We have different kinds of network connectivity, and then we have wireless standards, like we have wireless communication networks, like we have GSM, we have CDMA, we have so many different kind of technologies. So the communication technologies were there, and you have information technologies were there, operational technologies were there, manufacturing technologies were there, automation was there, so everything was there. But why suddenly these things are called as the fourth industrial revolution? What has changed now? Now why it is suddenly becoming a talking point? That is because there is a convergence. The convergence means now you are able to use them together. How is that enabled? What is the architecture? And what is the new application? So how are you able to do it? So let me just give you a perspective. So now, so we have phones, like all of us, we have smartphones. We call a phone as a smartphone. The reason why we call our phones a smartphone, because it can do multitasking. It can do so many things, right? So previously a phone cannot do other than just calling someone, your loved ones, your friends, families, maybe your work. So that's what people normally use phones for. Now you can use phones for anything. So you have expanded the scope and possibility of the phones because of the app ecosystem, right? So the app ecosystem has come, and then now you can have an app for everything. Now you have an app for everything, right? So to wake up, to go to bed, right? So to commute, right? So you have to travel, and then to stay, and then to meet, and then chat and listen, and to love. So you have so many things. So you can do so many things with the connected. So that is very important from the perspective of a smartness. But what is so smart about manufacturing? What is smart manufacturing? So my definition of smart manufacturing is this. Now, so we have a lot of modeling and simulation technologies, right? So we have data analytics and machine learning systems. So those things actually, you are able to simulate a particular manufacturing system or a product from variety of perspectives. Now you are able to have, the system is able to basically look at a proactive system. It also becomes an intelligent system because you can actually have lots of billions and billions of data points. You can actually construct actionable intelligence from the data that you gather. So the data is also becoming increasingly available because we have sensorized the entire world. So we have sensors everywhere. So sensors could be like optical sensors, like you have cameras everywhere, visual, like you have sensors which measures temperatures, which air quality. You see so many different sensors are being employed everywhere in manufacturing shop floor. Nowadays, there's a huge amount of sensors being employed. So billions and billions of data points are being gathered every day. And cyber physical systems, which actually is making the system more adaptive, and cloud and crowdsourcing platforms making collaborative. So for a smart system to work really well, a system should be able to, I call this smart because this is my definition which I published in 2011 in one of the prestigious conferences, which is the International Federation for Information Processing. They conduct this conference yearly. So we published this and gave the definition for smart manufacturing in the 2011 paper. So which I proclaimed that the smart manufacturing system should have a proactive capability, intelligent capability, adaptive capability, and collaborative capability. Notwithstandingly all these four only, but additional things. But these are the four essential aspects which converge to form a smart manufacturing technology. Now, what is this big data? So the big data is essentially about. So we have been capturing a lot of data. For example, even in our college, we collect so much of data. So their attendance data, the students' performance data, and then their classroom data. Then we collect data about their medical records. So we collect so much of data. So billions and billions of data points have been already collected. But only lately, technologies have been developed to basically create actionable intelligence from the data. So especially with the introduction of MapReduce by Google. So which can actually break down a very complex, very huge amount of data into small data and then provide that problem split that problem into small problems and solve them and assemble them back. So with the MapReduce and the Hadoop clusters, and then we don't need an HPC right now. So now what you can do with the HDFS file format, you can take any data, which could be unstructured or structured data, like structured data coming from a database or unstructured data coming from audio or a video, natural language processing, so or text, simple text, passage of text. So you can mine them. So you could actually create very actionable intelligence from that. So this all started from social data mining, right? So the social data mining. So I'm seeing some numbers in the chat window. I don't know what it really means. 587,073. I don't know. So anyway.
No, that is actually the participation registrations ID. So I request participants that not to post anything that is not required. If you have any questions, only those questions kindly you post.
Oh, okay. So you have a special ID for individual one?
Yes.
So this is additional data that you have collected. Okay,
yeah.
Anyway, so fine. So we are talking about systems which could be collaborative, which could be adaptive, which could be intelligent, which could be proactive, right? So now one of the things that I want to tell you about big data. Big data means like you are able to create a huge amount of knowledge from the data. So earlier we had a knowledge bases, we had inference systems, which together called as expert system. But that time we didn't have the capability to handle that amount of data. So billions and billions of data points. Also, they are disparate. They come from disparate sources. So you are able to do that. Let me just give some examples. So you go to a manufacturing shop floor. There's a lot of information systems. You have maintenance systems. You have supply chain systems. You have your information systems for design. So many things are there. So all these different technologies. So what we call as this, like information systems. Notification. Right. So now, yeah. So we have so much information. We have materials information system, manufacturing information system. We have management information system. We have supply chain, life cycle. We have maintenance. We have quality. Right. So we have packaging. We have dispatching. We have scheduling. So we have production control, process plan, CAD, design. So many, like we have a PLM system. So life cycle management system. So you have so much of information system. They all gather so much of information over time, but they never knew that you can unlock the business value of the data by using simple technologies like MapReduce. So that is why it becomes so evolutionary, because you are able to take all those billions of data points and feed into the system, and the systems gives you beautiful intelligence around you. Let's say, for example, I will give you a simple example. So earlier, there was an automotive case study where they were making some cars. They never realized that under winter conditions, when they are going to basically use some salt for melting the snow on the road, that salt would be little corrosive and then make the life of the products, a little, maybe it reduces the life of the products, maybe fails prematurely, right? So that influence was able to basically, they were able to get, because they had a traceability. They built in the traceability in the supply chain, so the warranty claims data, and also the production data, where the material is coming from, which factory, which slot. So they were able to do it so completely in a one single information system. So that kind of information system that it actually able to create a dashboard around it. So they were able to basically do the data analytics around it, and they're able to come up with an idea like why it went wrong, what went wrong, why this product fails prematurely, because they were able to pinpointedly tell that particular problem. So earlier you had design issues like design systems where you can have failure mode effect analysis, you have accelerated live testing, but still they could not have realized that that such a use case condition would be there. If you collect some data from there, if you have instrumented some sensors and then you have collected some data, it will be very useful, right? So we are not taking data from the use case like that is what commonly we call this as the instrumenting sensors in industrial IoT. So the IoT is enabling connectivity for everything. IoT is enabling connectivity for your assets in the factory, like not just your assets as well as your suppliers' assets, and then also in the use phase, what are products that are getting manufactured. So it is able to tie up very easily because we have instrumented a lot of sensors around it. So that is what we call as the big data and manufacturing intelligence systems. So, and also there are objectives which are becoming, in the first slide when I talked about the challenges. So there are a lot of new challenges, especially with respect to manufacturing system. Earlier, there are only 3 mantras people normally follow. One is good quality products in shortest product development time, right? Also customer focus. So you have customer focus for good quality, low cost, and just in time, or correct faster product developments. If you are able to bring products into market very quickly, good quality products at not cheaper rate, then you are successful. But the problem started when the climate change and like you had these restrictions on things. So let's say now, if you look at the factories, they have to constantly reinvent their manufacturing strategies. Just because suddenly there is a new law or new regulation. So they say that today, next year, we'll be completely moving the electrical vehicles. Just throw away all your IC engines. So it's a very disruptive technology. So suddenly one person says that today we are going to basically go with RoHS. So we have to do leadless soldering because lead is carcinogenic. So we need to basically move ahead. So essentially we are talking about disruptions and disturbances which is coming into the factory. So you are able to basically make a good decisions around it, right? So, and modeling and simulation tools are able to basically analyze the performance situations and then get the performance things. Prashant, how much time do we have? This talk is scheduled for?
Sir, till 3:30 we can go, sir.
Okay, 3:30.
Yeah.
So I just try to keep the time in mind and move a little faster. Thank you. So the collaborative is about cloud, and because we are able to basically take data and information as well as we call this as DIKW pyramid: data, information, knowledge, and wisdom. Right? So when you're trying to build something in the data, information, knowledge, wisdom, so you take some data and then convert that to add some information and then make that as a useful knowledge and then create wisdom around it. So now these things are available. So now you can now this wisdom is available everywhere. So now if you are able to create data and do analytics and create wisdom through cloud computing, you can access this. So you can actually make that as a service. So your knowledge as a service. We call this as knowledge economy, right? So when your knowledge becomes your tool to basically, rather than your muscle power, right? So we are trying to become a knowledge economy, means like we are able to create new IPs, new knowledge, new gain, new insights about markets, about products, about factories. So that would be basically shared. So through cloud sourcing and cloud computing. So you become more cloud enabled, and then we become cloud native or digital natives that they call, right? So that would enable the convergence of technology. This is what we call as smart manufacturing. So I very quickly say that smart manufacturing consists of the CPS, cyber physical systems, IoT, digital manufacturing, or digital threads and digital twins, additive manufacturing, advanced robotics, cloud computing, big data, right? So and integrating everything together for our objectives in sustainability and advanced simulation and things, right? So this is what we call as the smart manufacturing, right? So now, so we will get into the business drivers first because we are the topic of this entire workshop is about drivers. So we look at what is the business driver to implement any smart manufacturing or industry 4.0 in a factory. So the connectedness we already saw because of the everything is now connected. Your fridge is connected, your washing machine is connected, your bulb is connected, your speakers are connected, your TV is connected, right? Your heart is connected to your doctor through your wearable devices, right? So now your human organs are getting connected. So right, you have cows which are connected. So you are connecting everything to the internet, and the data is becoming pervasive, and that data is like being used everywhere. That is Internet of Things. The industrial Internet of Things is about getting plant-wide visibility and optimization. So you are collecting a lot of data from different shops and use it. So today I'm going to give you an example of energy information as a case study next that is coming up, right? So we are talking about plant-wide visibility and optimization as a very important aspect. And also we are moving from reactive to proactive and predictive maintenance strategies. So I think if you look at big data, the big data is widely used for in the industry 4.0 context. They are looking at it as a predictive maintenance strategy instead of, let's say, a reactive strategy like so don't fix it until it's broken, or that kind of philosophy. We are moving away from it and then doing a predictive and preventive maintenance. So let's say, let's assume you have a car and then you have a sensor and then you know that when to change the oil. So instead of changing it periodically, in a periodical maintenance where 6 months you change oil, but you have a condition. You know the condition of the oil by putting a sensor, and then when you need to change, you change it. So you know, suppose if you are not used your car during COVID-19, probably your oil is really good. Maybe you can run for another 3 months. So no issue. So why do that sustainability increases? Because you're not using an oil which is extracted. You're not using a fossil fuel derived oil or mineral oil, whatever it could be. Right. So we are talking about moving away from reactive to proactive, and also agile enough to handle critical orders. Now you see that we have seen now. So the large increase in what we call as I think I'm getting a lot of messages again with some numbers. I don't know what to do with these numbers. The chart message 45, 73. So Pankaj, I don't know what they want to communicate to me, but anyway, so you can, if you have any questions, you can put it, right? So if you don't have much questions, probably I will just go forward, right? So now, so there are some, so the organizers can put a message in the chat window. So probably they will be able to do it. So now if you look at it here, so when you look at a collaborative cloud-based apps ecosystem, right? So we are talking about a lot of app ecosystem, like in factories now you can have an app type of ecosystem, and also you can put your plant information to work, right? So you are able to basically take the information from the plant and then you can derive actionable intelligence from it. And also you are able to operate at the peak energy efficiency, because energy is becoming a very important thing because of the climate change, the regulations. Now you are looking at emissions and things. Sustainability is a very important thing. So sustainability is a 3-pillar model. We're talking about economic and environmental as well as social perspectives. So we have lots of metrics that we need to measure and then report. We have the corporate sustainability reporting. Industry needs to be very agile. Cut down their emissions, cut down the carbon footprint, and then move from fossil fuel energy to renewable energy sources. And then they are also able to efficiently operate their factories, and then that is what is forcing. That is one of the business drivers. And this one is very important. For example, right now we have COVID, so there was a need for masks, and also initially there was people thought that ventilators are essential, so people started producing ventilators, and then so the factories which are producing earlier were not able to cope up with the high demand because it's a critical order. So such a kind of they want to build a flexible manufacturing system is one. that is typically able to handle variety, volume, scheduling flexibility, sequencing flexibility, process flexibility. You have varieties of flexibilities that can be built, but they basically want to move agile or resilient enough, even though there is a stoppage in the production. There is a disturbance, means like there is a reduction in the demand. Or disruption means that's completely going to stop the production. So you should be able to basically handle those critical orders without loss of efficiency. Like in supply chain management, they usually call this terminology as something we usually call this as responsiveness, right? So responsiveness is about how quickly you can actually respond to a changing situation or situation. These are one of the things, right? So these are things which actually enabled smart manufacturing or industry 4.0. Now this is from the systems perspective. So whatever I have discussed so far is from a systems perspective. But what has changed from the product perspective? So this is the fourth industrial revolution from the drivers from the product perspective. So what is so important about the product perspective? Now, so let's just look at the first industrial revolution here, so which is about 1850. So when we had huge amounts of product variety, that is when the manufacturing, if you look at industry is mostly craft production. Craft production means like one-off products that will be made in a place. Like if you want to make a car, you go to a manufacturer, he may have a shop and then he builds one custom for you. So that's a craft production. And then in 1913, when Ford introduced the transfer lines, where there is a moving assembly line, they introduced this concept of moving assembly lines, which is called mass production, which is the second industrial revolution. In that, what happened is like they were able to basically, volume means like the quantity of the part that they produce or the number of parts that they produce. So they were able to basically produce the same number of parts, right? So one after the other. So I think you would have seen this particular, thing, like people can have the Model T in any color as long as it's black. So that's what entry force. So that means there is no customization. So because they were able to basically create stamping processes, metal forming processes, right? So they were able to cut down the cost, right? So they were able to make thousands and thousands of those same cars in a moving line. So they were able to achieve very high efficiency. That is typically what we call as, the mass production. Mass production is all about high volume, low variety. But the craft production is about low volume, low variety. So the mass production peaked in 1955 when you have the Beetle. Right? So the Volkswagen Beetle was the largest single model produced. So it's the highest number of single model car that is produced. So it's the highest mass produced car so far, right? So and then slowly people started to move from 1980s. They started move towards mass customization. So this is from the product perspective why industrial revolution makes sense. Additive manufacturing and all is included in fourth industrial revolution only for this reason, because people started moving from mass production to mass customization. This paved way for the fourth industrial revolution. Now what people want in mass customization means like you take the volume, same volume, but also with the variety. So you have high variety and then you are able to produce them at the same cost. Now the cost perspective is very important to understand. Let's say, for example, you have a die, stamping die. Let's say you are producing a car. Let's just go to a Ford factory which is just nearby, some 10 miles from here, or maybe a BMW factory which is just 5 miles from here. They have a stamping die which actually produces, let's say, the panels. Like you have the body in white, on top of which you have the door trims, and then you have the bonnet, and then the trunk, right? So you have all the sheet metal which is to be formed. The doors and everything should be formed from a sheet metal through a stamping process. These dies are extremely costly. Until you make thousands or thousands and thousands of parts from those doors, so you will not be able to get or recover that cost. That means you are amortizing the cost of the die over its volume. So that means you are able to produce large number. Then only you are able to basically get back that what you call as this cost. You are able to recover that cost. So that is the idea of mass production. So you have a shaving blades and all. So all the injection molded components, the mold is extremely costly. So you may have to spend a 1 crore rupees to just get a shaving blade, right? So for the mold, then you sell, let's say, 1 crore shaving blades, make them in that so that each 1 rupee gets amortized to 1. So unless you get that volume, you cannot change the design. So now, if someone is going, let's say, for example, mass customization, that means they want to change the variety, that they have to throw away this die. So that would cost huge amount of cost for the product. So it is going to be extremely expensive for somebody to make huge varieties of parts in one single factory, just because the problem is now they cannot use the conventional manufacturing process for that, because they have to amortize the cost over there. Now the additive manufacturing became a die-less manufacturing because there is no die. Which is additive manufacturing is you start with a single digital representation of the part, and then it could be any part, whatever your imagination you can model, any complexity. Now, so you want to basically bring more complexity. At the same time, you are able to divide and conquer. So you are able to slice those geometry into thin number of layers, and then you are going to make them layer by layer. So you have decomposed the three-dimensional complexity of the part into two-dimensional complexity. So that means the complexity has reduced considerably just because you are doing it layer by layer. So that's why additive manufacturing can handle variety as well as it can handle volume. As of now, it has certain difficulty in volume, but it can actually handle a lot of variety. So that paved way for mass customization. That's why additive manufacturing is also included in the fourth industrial revolution. So what is the driver? The drivers for Industry 4.0, which is your main theme of your workshop, these are the four drivers from the product perspective. So factories are becoming decentralized factories. So you want to produce something, the products has to be produced in a decentralized, distributed, personalized, and also complex. Let us just look at complexity from this particular perspective. So you put volume and customization and complexity in three different axes. So this is mass manufacturing or mass production. This is the second industrial revolution, where you are able to make huge volumes and make revenue. Right? So this is about the customization, where you are able to customize the part. This is about complexity. So you are able to create very complex products that were able to basically address. But this angle was very difficult in conventional manufacturing, because the moment you increase the complexity, there may be an issue with the mold. Part cannot be released from the mold. So design for manufacturability won't allow you to put so much complex things. But additive manufacturing, there are a lot of complex parts that you can produce, right? So now this complete manufacturing freedom about customization, about complexity, about volume was able to achieve in the additive manufacturing. That's why it is called revolutionary. So industry is want to basically exploit that additional cost that comes because of, let's say, redesigning it to make more complex and more customized. So that is what they are exploiting. So let's just now understood two drivers. One is basically this one driver which is about fourth industrial revolution, another driver about one about the system level, another about the product level. Now we will move into the reference model. Okay, so what is this reference model? So we'll just look at this as a reference model, which is called Industry 4.0 reference model. So here we are talking about a reference model for fourth industrial revolution, which is called RAM, reference architecture model for fourth industrial revolution. So which is I think roots in the Purdue model. We call this as ISA 95 model. Now, I will try to basically try to bring this in the case study. Let us assume that you have a factory, right? So you have several layers. You have assets which are integrated through a communication network, where you collect information about different functions and report it to the business. Let us assume that these are different layers. And you also have physical hierarchies, right? So we have product, then field, control, station, work center. Like it would be something like, I would say, a line, which has a product is a work in process is there, and there's a field control device, right? So and then you have a workstation, maybe a painting station, or a, like assembly station, probably engine stamping station, and then you have centers, and then there's an enterprise, and then you have multiple factories which are connected, right? So this is the physical hierarchy. IEC 625 is standard, which is physical hierarchy. And this is life cycle. So I'm just trying to put a very simple perspective. There are three major domains which you can talk about. So one is typically a value chain domain. This is a value chain domain. So this is the life cycle domain. This is the enterprise domain. So you have so many things happening. The value chain is about suppliers to customers, where there is an information flow and financial flow. And there is a life cycle, which is like design to disposal or raw material to recycling, whatever you can call. This is a life cycle of a product or life cycle of a material. Both could be represented in this axis. Then you have enterprises, where you have shop floor to business, right? So now there is an information flow happening along this. There's an information flow happening along this. Here there is a product data, and then you have performance data, maintenance data, so many data flows along the life cycle, design data, analysis data, testing data, prototyping data, so many things which flows along through the PLM. And then here suppliers, logistics, warehousing, user, customer to supplier. So you see the entire supply chain information going on here. So this is about shop floor to enterprise. You measure operational data. There are 4 levels. This is the ISA 95 scale, right? So this is the physical hierarchy level. So now let's just give you a reference model. Now what is this industry 4.0? I'll just give you a simple idea. So if you want to understand this reference structure, suppose you want to measure energy. So energy is an information that we want to measure. We have instrumented some sensors, maybe power sensors or maybe current sensors or whatever it is. We are trying to measure. So you have a one-plug efficiency. We also developed a product called Nbox. It's an IoT tool which can actually get you, ISO 15000 energy management standard certification automatically. So it's a patent pending IoT device that we developed. But let's not go into it. But let's look at something like this. We want to measure energy. The same energy information could be used in different places. Like in the value chain, that energy information could be used to basically tell the customers about how much energy consumption. Maybe the customers want to know about the eco level. Let's say you have developed a product like refrigerator. You want to measure energy and say how much energy efficiency is there, and then obtain the eco star label, right? So that would what customer want to know. That is one way to measure energy. In life cycle, people want to do the life cycle analysis. Let's say they want to understand the total carbon footprint. So they want to take the energy at different stages, and then life cycle analysis is LCA is a 4-step system, which is ISO 14044 standard, where you do first whole and scope definition, where you want to define the goals. You can either do a cradle to grave full life cycle or gate to gate, only manufacturing stage, raw material stage, distribution stage, or use stage, or recycle stage. You can actually get the full perspective. Then once you define the goal and then do an inventory analysis. Inventory means like you have measured the energy in each stage and then create a virtual workflow or flow chart of those reference flows, and then you create all the energy used, material used, water used, and emissions to water, air, and land. Once you measure all these things, you can get a good picture about how that, what is the impact. That is the 4th step, impact assessment. So 3rd step is impact assessment. 4th step is the interpretation. Right? So in impact assessment, then you say how much of this energy that is used can be proxy to carbon footprint or global warming potential, or how much this could be like CO2 emission could be also used as a means of understanding acidification or probably SOx emissions or NOx emissions, which could be also used to understand water eutrophication or maybe natural resource depletion or deforestation. So many impacts that you can study. That is about life cycle impacts. The same energy information that you measure from the sensors is seen for eco labeling, or from enterprise somebody looks at obtaining an ISO 15000 standard for the plant for energy management, or probably paying the electricity bill, understanding it. So they may want to do the baseline studies on the energies and then try to improve the factory energy efficiency, cut down on the cost of electricity bills, and also the corporate social sustainability reporting. They want to report about their energy usage, reduction in the energy usage. They also want to get tax credits. Like enterprise and business people always worried about money. So you have to convert the energy into dollar terms in terms of how much input tax credits that they can get. Because when you cut down on the fossil fuel emissions and also your energy usage, you get tax credits. So that is energy money savings for the people, business people. So, and also the energy that you measure can be also used in the shop floor person. So he can be used to operate, optimize the process around it. Let's say the MRR can be adjusted. You can just simply use a current sensor and do two-layer monitoring, and then you can do. So like technical people on the shop floor, machine operators and operational people. So you have 4 levels, like you have level 0, level 1, level 2, level 3. Like operational level, what are the information? Like you can use scheduling and sequencing and dispatching rules based on the energy usage and emissions and things like that. So because OSHA is an organization called Occupational Safety Hazards and Emissions, or Occupational Safety and Health Administration, they may come and shut your place if you're not following emission standards. So they need to constantly monitor for it. Operational people has to do that. So you see that, so you use only one single information, but you take into disparate information systems like life cycle information system, value chain information system, enterprise resource planning system, ERP system. So you are able to use that information in and also integrate it for multiple purposes. That is what is typically known as the Industry 4.0 or a reference model. Now you have a development. This is the from product design and development to maintenance. This is a use case. So this is the life cycle phase, right? So this is the life cycle and value stream that we are talking about. Then you have physical hierarchy in the enterprise domain. For different layers, you have different kinds of this, algorithm that work with. So you have different layers. So let's say you take a simple asset The asset could be something like your a small machinery, or it could be a dump truck, or it could be like a forklift truck, or it could be a conveyor belt, or it could be a robot, it could be a CNC machine, or it could be a pallet, it could be AGV, it could be anything, it could be ASRS, it could be something like your lights and HVAC systems on your factory, and it could be anything. So that's what I'm talking about. So assets, and then you have you have to collect the integration information and then collect and communicate that information to variety of functional people. So functions could be so many different functions are there. Like you have a function like design, R&D, the packaging, quality, maintenance, asset management, and then you have marketing. You have so many people. So all of marketing people need to create a eco level and then communicate that information to the stakeholders, right? So business people has to get tax credits and submit quarterly revenues and quarterly information about it, how much energy they have cut down and things like that. You see that? So that is what is the reference model. So Industry 4.0 means that everything is orchestrated. There is no one single person going into individual shop floor and collecting information on a paper. So you are trying to basically create a revolutionary system where you are basically take any data from any sensor and roll up that to multiple KPIs. What is KPI? KPI is key performance indicator. So the key performance indicators could be for anything. It could be something like what we call as OE. So OE is the three important metrics like availability and quality and your production schedule. So it's the time related metric which is rolled up into cost, right? So OE is like overall equipment effectiveness is a very important metric. So now people can build beautiful dashboards. Now the dashboards are built all along the factory by collecting sensor information. I'm just telling about only one information like energy. Now there are so many sensors, so many information is being collected. And if you're able to gather this information and put them into a dashboard and people can visualize, that is one step. And then take the data and then do analytics on top of it, then it becomes another level. So this system becomes intelligent. And then you build controls, like we have CAPA, like corrective action, preventive action plans. Then it is again another level of control. So you go to a context sensitive, right? So situation aware system where this information from variety of sensors through IoTs are captured and analyzed, and then intelligence is enabled, and then it automatically does. For example, the IoT system, the inbox system I talked about. So what you need to do is you need to buy this inbox from us, and then you take the plug from the wall and then connect the plug to the inbox and then connect the box to the plug. So it automatically sends through that energy information to my cloud. So 6 months I will monitor that energy usage. Then I create a baseline. Then I use, that is called, I call this inbox because it's called energy baseline of X. X is a thing, right? So X is anything, right? So X stands for a thing, X is a variable. So inbox means energy baseline of X. So that inbox can be also called as environmental box if you want to put any other sensor, but it's an inbox. So then that information is being gathered over 3 months, and then that is used as a baseline. Then another 3 months data is collected if you have done any intervention, right? So and your energy usage has come down from the last 3 months to the present 3 months. Then you have something known as a ISO 50,000 certifications that can be provided, because you don't have to send an energy auditor or inspector to the place to see how much energy they do. You don't have to take their electricity bills and then analyze nothing. So everything is orchestrated. So this is typically called as the Industry 4.0, or what we know as the fourth industrial revolution, where all of these things plays together. Now where does this advanced simulation come? Because you can simulate this process and get the KPIs upfront. Like you can see how much performance degradation will happen if you introduce a small disturbance, if you introduce a small disruption, or if the energy price goes down. So where are the other options for available, things like that. So people are able to basically do a variety of scenario simulations. Then they become proactive. Then also they are able to connect it to cloud, and then the data is connected in a common place in the cloud, and then the information is being fed back in the form of a dashboard with all the intelligence that is being gathered is presented to the people who are going to make the decision. And sometimes the decision can be themselves made. Like there are social networks for machines. The machines themselves do a reactive scheduling based on, so I'm down, can you just do this job? And then I'm just rerouting the job. Real-time rescheduling. So we published last year a paper on real-time rescheduling, reactive rescheduling. That was based on MT Connect channel. So something like this. So there are a lot of things that. Now we will have very less time, so I will not go very deep into enabling technology, but I will try to introduce them. What are they? But anyway, you will have the entire, probably this I 4.0 webinar to cover all these topics, but I will give you a glimpse of how this is being applied in manufacturing. So what are those enabling technologies for the fourth industrial revolution? We saw the 8 technologies, right? So I'll quickly spend 2 minutes on each of them and try to explain, and then finally I'll give the benefits of Industry 4.0. Now the first one is Industrial Internet of Things. So Internet of Things has 4 major elements. The first one is the data, which you are going to collect, which is collected through a sensor, right? And then there is a wireless communication, there is a network, right? And also there are applications which actually uses the data in the cloud, or maybe in the local cloud, or maybe in the local computer. So you have network, you have data, you have sensors, you have cloud. So these are the 4 major layers. So we call these as layers. So what is the use of them in the factory? What is the industrial Internet of Things? But they have been used in cars, then vehicular industrial IoT, and then medicine. You have medical things and all are available, right? So you have so many things. So you have a predictive maintenance. As I said, some of the metrics like key performance metrics like overall equipment effectiveness, mean time between failures, performance optimization. You can learn analytics and KPI can question a dashboard. So if you look at the pillars, you have the communication at the bottom, like all the communications, right? So then you have near field communication, social networks, internet, 3G, 4G, Wi-Fi, WiMAX, all those things. Then you have semantic web. Semantic web is about it's about the internet of knowledge, right? So we have seen the internet of pages. So you have a hyperlink, when you click, you go to the other page. That is what the internet is all about. So you are connect what we call a semantic web. So you are able to create a open data and then also give meaning to them. So for example, you can take an entire Wikipedia information and then connect them to a graph, so that the entire knowledge about the context information can be very easily obtained. So that is what we call as a cognitive IoT. So that is typically called as the intuitive IoT or a cognitive IoT. Cognitive IoT means like you are able to contextualize any information. Like for example, you are taking a data, then you can connect the data where it is come, which part, and then why it has come, and then what is the reason. So everything can be connected through semantic web. Semantic web is a resource description framework. It's a 3-tier model which uses a web ontology language called OWL. You can build beautiful applications around semantic web and Web 2.0. Then you have wireless sensor networks, barcodes, and smartphones. Then you have RFID, CMOS, like you have all those communication sensors that you can collect data from. So this is what is IoT. So these are the 4 layers I talked about. The first layer is the sensing layer, second layer is the network layer, third one is the service layer and interface layer. In sensing layer, you have a lot of sensors which could be reading the data and then transmitting data sensing and equations, transmitting through cloud and reading the data and then transmitting data sensing and equations, transmitting through cloud. And then you have service. So you can build beautiful services. Maybe dashboarding is one service. Probably another service could be like dispatching service. It could be like a scheduling service. It could be something like warranty claim. It could be anything. So you can build so many different services. You can build a lot of applications and then interfaces using APIs, application programming interfaces. And then you can use service-oriented architecture. That is what we call as SOA. So you can use the service-oriented architecture and then build these services. That is what SOA means. You can use it. This is a simple idea of industrial IoT. Now, cloud means like you can actually servitize using service-oriented architecture. For example, right now we have lots of people whose factories are being unutilized because COVID is there. Suppose if it is connected through cloud, you can operate it from something. You purchase license for ANSYS, then you can you are not using it 100% of time. You can servitize it to some people. It is like you have a car and then you tell Uber to basically use it when you are not using it. So something like that. So you are creating a cloud-based service discovery system, and then with that service discovery, somebody discovers that you have available service, and then you take the service and do it. So this is what is service-based cloud, customized production-based distributes. Like you can create a design service, purchase service, assemble, logistic, milling, 3D printing, and then you have an internet service product through which you are able to connect to individual 3D printers, CNC machines at the asset level, right? So, and also the data is very important. So whenever you are trying to basically use the data has to be properly done. So there are a lot of characteristics that people call the 6 V, like volume, variety, volatility, validity, velocity. So they call the 6 V's, right? So even people explain up to 16 V's, right? So so these are all different examples of data. So data has to be transmitted, and then it has to be extracted, transformed, and loaded. We call this as ETL. So this data could be about a person, about an equipment, about a product, about the management or operational, or maybe interactive data which is coming from, let's say, your HMI, your SCADA system, or maybe from your distributed control system, whatever it could be. So you have a manufacturing data life cycle, which is essentially coming from here. So this is the Internet of Things. This is the communication network, right? So this is the internet and this is the data. So the data could be used in design, manufacturing, MRO for variety of things, fault prediction, maybe decision support system, right? So maybe for market forecasting, maybe demand analysis. So you have so many things. You can create a chart, a graph. You can also put that into virtual reality headsets, right? So you can visualize it, you can print it, you can publish a report around it. So you have result visualization application. So this is what is Industry 4.0. So you take a data and store the data and collect it and then put it into the web, process it, and then use it in a particular application. Now simulations are there, widespread. This is another important thing about Industry 4.0, advanced simulations. You can simulate your robotics movement, the factory layout simulations, systems planning, ergonomics, right? So product design simulations, network design, operating, energy, sustainability, and all those simulations. Simulations provide you a foolproof way of operating a factory. So simulations can completely, design. For example, GE has very sophisticated simulation systems. Can simulate the entire factory, and also from multiple scales, like looking at the time scales, looking at nano level time seconds per seconds to per year. So you have different kinds of production planning. You would have studied about aggregate planning to master production scheduling to like MPS, and then you have individual scheduling and planning, and then production planning, and then process planning, and then activity planning, then to task planning. So you have so much granularity with which the planning is done. So simulation helps you to plan that. So you can orchestrate everything. You can see how the data is collected and where it will be faulty. So you can build the factory in a fail-proof way and operate the factory in a fail-proof way, because you become more proactive, because you run the simulations to see whether there is any failure that is going to happen. So that is what is. So and you collect a lot of data. There are data historians. You store this data in a data historian and use them often. So. And AR/VR has a lot of applications in, like I'll show you some applications in training, in design, in manufacturing, in operations, in service, sales. So what is the use of AR/VR? Why people are talking about AR/VR? Because why they are calling it as a evolutionary or revolutionary technique? Because we have in our smart manufacturing center, we have multiple AR/VR equipments. Like we have HTC Vive, Oculus Rift, we have cave systems. So what essentially we do here in this smart manufacturing is like we build augmented interfaces, because right now whatever we do, the artificial intelligence techniques can augment many things. It can actually augment us in a real world situation. For example, here you can just see a factory. So it tells the process capability values of each of the machines. So it is able to localize the data and then quickly visualize. So if you give numbers, let's say machine 1, machine 2, machine 3, you may not be able to understand it. So you can see a person and see how much injury loss due to injury he has had, how many leaves he has. So it's like it is able to recognize and contextualize the information and present this information for management to take a decision very quickly. So you can see that the red line has a very poor capability index, and then whereas the green one is operating normal. So people are able to do interventions based on that. Also, it could be used for diagnosis, it could be used for maintenance and things like that. So this is augmented reality. Additive manufacturing, as I said, people are beginning to use. With Prashant, probably I will take 2 more minutes. Is it okay? If I run 2 more minutes, I have.
Yeah, sir. Please carry on, sir. Carry on.
Okay. So if I look at additive manufacturing, so people have been looking at standard design. So standard design means like they are looking at one-off designs as a very costly effort, because you cannot make same product with a different variety, right? So that is because your production methods right now, whatever you have, doesn't enable that. But in additive manufacturing, because of the design can be changed, you get a lot of complexity which comes for free. That means you can customize the product, you can have a lot of varieties, you can, but at the same time, you will be able to basically cut down the cost. So, but in conventional manufacturing, the cost would have skyrocketed because you have increased the design variety or design complexity. But here, because of that, there is no increase in cost, even though there is an increase in the complexity as well as increase in variety. So that is making this. Actually, I have a lab called DFAM lab. In fact, I run a 40-hour course only on not on additive manufacturing, but on design for additive manufacturing. There are so many tools, like we have topology optimization. I will summarize that maybe in this particular slide when I come to that. I will not take much time. So essentially what I'm trying to convey this here is that when you have more complexity, that complexity comes for free, because they want to tap into this. They want to use topology optimization, generative design, functional integration. They want to use multi-materials, hybridization, hierarchical complexities, material complexities. They want to increase the structural complexities. They want to increase geometric complexities, and even look at complexities in design. So in fact, in our two of my PhD students have developed a complete decision support system where you can go to a factory and ask their parts and load those parts into that, and it will tell you what is the feasibility and viability to move into AM, and it will also tell what are the redesign possibilities, so that your cost can be coming down and you can customize the part and then move the part for AM type of situation. So those things, decision support system, we have built complexity metrics and things like that. Right. So this is now the last part is about benefits. What are the benefits? Looking at from the system perspective, because we have been looking at from the systems and product perspective. From the system, you have higher efficiency because you have increased automation and fewer people in the factory. But you have people to set up the factory, but not inside the factory. Faster decisions and fewer people, lower cost. And you are able to basically increase the agility because you have responsiveness, as I said, immediately when there's a change in the schedule. So you are able to quickly realign because you have the fullest visualization built for any scenario of production. So you can just go and plug in your data, and then you are able to see how your performance data is there in the dashboard very quickly. And because of the proactive nature of the simulations, you are able to become more agile. So with the short lead time and very high mix of products is also possible. And also innovation. See, as I said, you are able to introduce new products into market very quickly. That's a full-scale visibility. We call this as visibility in supply chain, which is very important. And also, you have rapid experiments can be possible in the virtual world before you actually implement that. So innovation is improved. And also, you have full visibility. Customer gets to know everything because customer knows about every details of the product because he's also part of that. And he's also, in turn, giving the information back to the factory about its products usage and services that could be exploited from the viewpoint of improving the product performance over the next iterations of the product. And cost, like you have fewer people, less wasted material, higher initial quality, lower operating costs. These are from the perspective of operating costs, right? So I initially told about the capex and opex. This is about the operating expenditure. The revenues, you have larger markets, higher value products and things like that. But if you look at product perspective, so because as I said, there is an increased complexity. So you can have a very good form complexity, hierarchical complexity, material complexity and functional complexity because you are able to consolidate parts together. With additive manufacturing, people earlier were forced to basically make straight holes and they cannot remove the part from the cast mold or injection mold, die casting. So there are a lot of limitations, right? So now because the additive manufacturing can handle a huge amount of complexity, you don't have to give draft angles, internal walls. You can have thin, thick sections without having any issues. You can also have very geometric freeform surfaces. Large aspect ratios is possible. Different wall thickness combinations because in injection molding you have to maintain the same wall thicknesses throughout because otherwise warpage would occur because the differential cooling is differential thicknesses. You can maintain small gaps between features. Also you can have irregular porous structures. The structure is more organic, more biomimicking, right? So you can have mesosclepic lattice type of structures, foam structures. You can have textures, and then you can have a very small wall thicknesses and honeycombs, right? So you can also have continuous material transitions and all those things. So all these things are possible. And also you are able to consolidate parts and then embed foreign components. Now we can, because IoT I'm talking about, we have in our lab developed a lot of new technology around, by combining electronics into mechanical parts. So you can now build a complete IoT system on top of the mechanical part in one single 3D printing process. Now the IoT is combined in the same manufacturing process. In additive manufacturing, after I fabricate the part, then I use a micro-dispensing system to use conductive ink paste to basically deposit an antenna and then RFID circuit. So I have a RFID receiver. This is a wireless RFID. So I have a receiver which actually sends the power. So it's an energy harvesting RFID antenna which gets the power and then powers the sensor. The sensor gets the data. And then again, I have another RFID antenna on the other side, which there is a RFID receiver which receives the data. So you see that I have no connection of any power whatsoever. I just have a RF receiver and RF transmitter for transmitting energy and RF receiver for receiving the data. So I just draw this circuits by using the same in additive manufacturing process. That is what we call as foreign components. You can put active devices, passive devices, IC chips, even relative motion components, and the self-assemblies. You can have so many things in additive manufacturing. So that is why it is becoming more revolutionary thing right now, right? So this is possible. So what are the benefits? As this is the benefit session, so I'm just telling you the benefit. You have a reduction in design fade, you have improvement in isolation, damping. For example, if you have a lattice type of structure, you can have a very good damping. So each one of these piece In fact, I have 7 PhD students working. Each one of them is looking at energy absorption from an angle, heat transfer improvement because of topology optimization, aesthetics because it's more organic, and there is also a weight reduction because of the introduction of lattice structures and things like that. And also ergonomics improvement, outer flow dynamics because we are able to take conformal coolings in additive. Earlier we have only drilling can only have straight holes. When you pass liquid, it cannot cool efficiently. Now you can have conformal cooling channels. There's also heat transfer improvements, right? So there is also flow dynamics you can have, and so cost reduction is also there because we are consolidating the parts. You have higher the cost of assembly reduces, logic cost reduces, quality, manufacturing, all costs gets reduced. In turn, it reduces the sustainability. So this is the benefits. So finally, I will give you the research gap and then end this session here. So this is the current manufacturing system, and until this point, what we call as our conventional manufacturing system. So we have done a lot of digitization. We have islands of automation in all like CAD, CAM, CNC, like inspection, and then we also have in operation like dispatching, scheduling, operating. We have a lot of information system. They have been the digitalization has already happened. So we are no more using papers in many factories. And also the communications has been already built. They are already available. And also a lot of standards have been already built. Right? So, but flexibility in some automated assembly system is not yet built. Standardization in some awesome, but in single cell stations, these are built. And also in SIM, we call SIM that flexibility is not even built now, but reconfiguring management is not yet built. So these are several manufacturing system concepts currently in use in many manufacturing factories. But what is Industry 4.0? This lower one is the low-hanging fruit, and higher one is the ultimate objective. This is a utopian dream where there is no human intervention. The machines will take care, artificial intelligence will take care. We just get our share of machines' work. So we don't pay machines, but the machines pay us every month a salary. We just sit back and relax and watch a movie and then live in a utopian world, right? So we don't have to go to factories and work. So that is the self-configuration, self-optimization. Like the complete machines takes the production and then it just does its job on its own. Then we just don't have to do anything. So that is like the higher vision of Industry 4.0. I would say now it has become 5.0. Recently, I have seen 17 papers which has come up in recent journals, which is called the human angle they want to bring in because the humans is going out. So that is Industry 5.0, but I will not jump into that bandwagon right now, right? So this is what. So we are trying to have systems which can make decisions, which are early aware. Like early aware means like they are able to make predictive decisions, and they are also able to self-optimize and self-configure themselves, like self-healing materials and things like that. So 4D printing and all those aspects are coming up in Industry 4.0. So essentially, we are talking about systems which can actually operate by themselves. They can configure themselves. They can optimize themselves, and that is the higher level of Industry 4.0. So these are the research things. So I think when I change the dates, the initial slide, I think this is the correct date that I get. Maybe in the final slide I got the correct date. Okay. Anyway, so I think there are some questions which I would like to answer. Like there are some questions, sir. Could you please explain cognitive IoT? So I will give you an example. Cognitive IoT is about contextualizing information. Let's say, for example, cognitive IoT is about intuitive IoT. So let's say an IoT system. Let's say you have a NLP language processing. Like you have a sensor which is gathering your voice and then doing something. Let's say it's like you have a speaker which is IoT speaker. Now the simplest example is your Alexa speaker. So you'll be able to understand it much better. You have an Alexa speaker, right? So right now you're asking your Alexa speaker a question, like I want to, so I want to go to Paris, right? So for my Valentine's Day. So can you see the tickets? So that is the question I ask. So Siri or Alexa would immediately give something like Paris Hilton. So she's nowhere related to what I am trying to search for. But in a context sensitive, in a cognitive IoT system, so it has understood my natural language. Right, so there is an NLP algorithm. It also done the machine learning. So it understood that it's on a Valentine's Day. So maybe it will ask me like, you want to book a hotel, you want to book a reservation table, right? So it also asks you like, do you want to basically arrange flowers in your room? So see that. So that is what is contextual. So it is able to basically take my information. So if you do a simple web search, probably you will get a Paris Hilton as a Twitter page or something which is she's a celebrity, because that will be the result which is coming up first. And then if you ask, let's say, a simple little bit intelligent system, if you ask it, maybe it will give you, let's say, flight tickets, Google flight tickets, which is giving. But a fully sensitive, fully context-aware, situation-aware system, which is called cognitive system, where cognitive IoT is about building the intelligence into the system. So it is able to understand the context in which I'm asking the question. It is also understands because it has gathered billions of data points around me. Like it knows that is my anniversary date, and it also understood my preferences for a hotel room, like what rooms I like, and then also it has understood my preferences for a class of travel that I want. It also understands, let's say, the flowers that I usually buy, and also it has got a preference for, let's say, the hotels that I regularly go for, or what I like. So it is able to suggest something for me. So that is typically what is known as cognitive IoT, right? So cognitive in a factory floor, I would say something like, I ask a machine about, can you tell me what is the tool failure rate for this class of batch of process of parts? So that is the natural language that I'm interacting with the machine. So it has got an NLP algorithm. So it understands the context. It goes back to the data, hundreds of data. It goes to the data custodian, data historian, gathers the pulls down the data, and then looks at the tool cost and be able to tell that, okay, so right now you are operating at 10% tool wear rate for the current tool, but your job may be anytime broken. So I am expecting it to fail in another 10 minutes. Why don't you get prepared? And also the guy who is going to supply you, he is actually out of business for COVID. Could you kindly get a new supplier? So service discovery has to happen within short time, and your supply chain has to change. So there is also going to be reduction in the number of parts because the supplier service capability is very poor. So do you understand? This is what is a context sensitive industry 4.0 system. Do you understand? That is what we are talking about in a cognitive IoT. I think so. You are able to understand it, I think. Right? So, and also another one question: if industry 4.0 is implemented, engineers might get jobs, but what about workforce? They are our consumers, right? What will be the outcome of COVID-19 in Indian context in manufacturing? I think COVID-19 is going to basically strengthen the Indian manufacturing. The reason is because there is already a lot of manufacturing base that is being shifted to India, and also there is a lot of promotion of Indian SMEs, especially with augmented funds and things like that. So it is going to help. The COVID-19 would help Indian industry to strengthen its production capabilities, and also it is going to improve its production scenario. About the jobs, so engineers might get jobs, but what about the workers and the other communities? Okay, so I will answer this from two different perspectives. First of all, I'll take the example of a simple servitization like Uber or like Swiggy or probably something like Zomato. So they produce a lot of jobs, but these jobs are not high-skilled jobs. But it's an automation. Like earlier, the businesses have found a lot of improvement. Like people are able to comfortably travel from place A to place B because of Uber or Ola. Many drivers got their job, and then it created a lot of new jobs. But it is an automated system, right? So it is a servitization system. It's a cloud-based system. It connected people together. So it actually connected supply and demand. So, but it created a lot of unskilled labor. Now people who are actually engineers, they went on to Swiggy as a delivery boys, right? So, but that is what not we are looking at, right? So we are looking at people. We are looking at high-skilled labor, high-skilled engineers who are able to basically create next-generation factories, operate remotely factories of across the world from here, and able to connect and take data and do. So that is what we are looking at. We want to develop the next generation of big data technologies, next generation of artificial intelligence technologies. At the same time, we don't want to implement it in India as quickly as possible because there is a demand worldwide. Why you want to implement in India? Because when there is a large workforce available. So you use the workforce here for the jobs that you create, but you also create a high value jobs. So that is what it is. That is what I am talking about. So I hope I answered the question. So don't implement those smart factories in India, but have the know-how, develop the technology, and implement everywhere around the world. And then when you have done with your skilling, like you have done with your skilling for the jobs and also probably that time you would be able to basically get that high-skilled laborers into the high-skilled market, right? So that is always going to be there. So I think US, if you look at that, there's a knowledge economy that they are able to move from a labor-oriented economy to knowledge economy very quickly. So we will be able to also do it. It's a very short span of time, but there should be a push. So that is what we are looking at. So thank you. I think. So is there any other question? So I think Sunil Prashant, happy to listen to Senthil sir. Okay, so you were my student previously. Thank you. So I remember you. Yeah. So any other question? Is it necessary now to change the academic mechanical engineering towards? So it's a very important question. See, I'm telling you. So look at University of California. Look at MIT. Look at Stanford. Look at University of Cambridge. What they have done away is like now they have introduced programs called so they have introduced programs called engineering. There's no mechanical, there is no computer science, there is no electronics, there's no civil. So civil plus electronics becomes avionics, mechanical plus electronics becomes mechatronics, IT plus manufacturing becomes smart manufacturing, IT plus electronics become we have this hardware, and so you have so many different new fields which has come because of the marriage of technologies. Now people don't want to constrain themselves to the syllabus. Like University of Cambridge has stopped giving degrees in the name of mechanical civil. So now you go to University of Cambridge at undergraduate level, what if there is only an undergraduate in engineering? So people are able to then choose and study. So suppose if somebody is really interested in civil engineering, but they want to do also interest in electronics, they can do systems, like you have a lot of such things are coming. So now that is what I'm saying. So my question is, like, my take would be, don't change the academic nature of mechanical engineering. Never talk about academic. It's not about changing. It is about adapting. So it's about agile enough to basically change. Now they are able to change, but we should also able to change now, because now without data, understanding data, without writing code, no. So now if I ask my mechanical engineering student, ask them to code, they always say, no sir, I'm a mechanical engineering student. I don't like computers, that's why I came. But without computers, you cannot do anything. Because now, so that is why I'm saying that people have interest, but they should be also able to explore on their own. So the entire academic curriculum and everything needs to adapt. I'm not going to say change, but they have to adapt to the changing situations. Otherwise, they will become irrelevant in the context of the new requirements that industry really wants. So that is why many people want. So even IIC Bangalore. So in fact, we started in 2016. IIC Bangalore started in 2019. I think last year they started MTech Smart Manufacturing. So we were 2 years ahead of IIC to start it. So that's how actually, so people will follow. Now that time when I started the program, there were a lot of questions. There is no GATE syllabus, no big institutes like IIT is doing and things like that. So, something like, so they are talking about those, right? So now we are talking about that context. We are able to understand now. Now artificial intelligence BTech degrees have been opened in all the NITs and IITs. IIT will also follow. GATE syllabus also. Now they are saying the GATE syllabus you are not following. Now the GATE is now introduced data analytics, data algorithms, database management systems in production engineering paper and things like that. So the things will slowly change, because you have to become the first change so that people will be able to get jobs. I think we have got a good reception for our programs, educational programs that we have started. Also, our research programs are getting good funding from the Ministry of Education and things like that. So I think that's a good positive trend that is happening. So hopefully we'll do best. Thank you all. I think if there are any other questions, you can leave it to the
Thank you, sir. Thank you. So,
forward it to my mail ID. My mail email is also listed, so
yes.
you can always write to me. So if you have any questions, and also we also conduct a lot of useful sessions. Like we have a full course on Industry 4.0, 40 hours course. We have a full course on additive. We have a full course on IoT. So you can actually register for the courses if you want. You can come here, and then after COVID gets over, you can also travel and see. Like NITI students came here and spent a lot of time. We also have a makerspace. We have 18,000 square feet makerspace. We encourage DIY projects. You can come back and do a lot of IoT projects in our campus, and then I give an open invitation to all of you. Thank you all.
Thank you, sir.
Thank you.
Thank you for that excellent presentation. And you have touched upon each and every aspect of Industry 4.0 from global as well as India's perspective. So on behalf of all the participants and the organizers, on behalf of Nitty Meenakshi Institute of Technology, I extend a heartfelt thank you.
Thank you all for joining and have questions, listening. I think thank you for joining. Thank you.
Thank you, sir. Thank you. I request all the participants to kindly give us your feedback. The feedback link has been posted in the chat box, so I request you to access it and provide us your feedback. And also regarding tomorrow's session, the session will start at 10 o'clock. The link for the Google Meet link remains the same. We will be sharing the YouTube streaming link half an hour before the scheduled time. So if you have any queries regarding the sessions and all those things, if you have any queries to the speakers, you have our email address, so mech.ftp@nmit.ac.in. So kindly write back to us. We will try to reach out to the resource persons and get back with your answers. So with that, I would like to conclude this afternoon's session. So I would like to thank each and every one of you for joining us. So see you back tomorrow. Thank you. Thank you, one and all.
Thank you all. So thanks for the opportunity provided by the NITI, and also I congratulate NITI for organizing such a informative program and also enrolling so many people. I think it's well appreciated. Thank you.
Thank you, sir. Thank you.